Hi, my name is Nick Sean. I'm going to be presenting here my final project for Electrical Engineering 435 Deep Learning Fundamentals. So this project was looking at doing deep representations using autoencoders of smartwatch accelerometer recordings from individuals with Parkinson's disease. So before I get into details about the networks I used and the data I used to train them, I want to talk a little bit about the context here. So there's a lot of interest right now in trying to use wearable devices like smartwatches to monitor symptoms of Parkinson's disease. And these symptoms include things like tremor, shaking, rhythmic movements, bradykinesia, slowness of movements, and difficulty initiating movements. And both of those symptoms are really common, and they're often treated with a medication called levodopa or other similar medications, which unfortunately can also have side effects of dyskinesia, jerky, uncontrolled, unintended movements. And so there's a need to strike a fine balance between the two. And so being able to monitor these symptoms unobtrusively in the home would make it a lot easier for clinicians to balance how much medication to give and what the right dosage is. So one of the reasons why it's still really challenging to try to do that kind of monitoring is that symptoms like tremor can come in and out fairly frequently, even within the course of a few seconds to a minute. You can go from having symptoms to no symptoms and vice versa. So for example, both of these recordings here came from the same individual around the same time. And at one point, you've got very low activity, just at rest, no real tremor going on. But then a few seconds later, you have really significant tremor happening. And unfortunately, usually the only kind of information we can get here is that sometime during this whole 1 minute period where they were sitting, there was some tremor of some kind, but it's really difficult to pick out which portion of that was actually tremor, and it's usually not as obvious as it is here. So we need some sort of way to distinguish between the two. So that's where they got the idea of using some sort of autoencoder to reduce the dimensionality, make it easier to visualize, and maybe cluster the data and pick out which portions of the signal actually represent tremor and which ones don't. So the first architecture that I played around with was just pure convolutional neural network. So it goes from having a really long vector representing acceleration magnitudes, then going through several one-dimensional convolutions to reduce it down into this much smaller encoded vector in the middle, which then through the decoding layers is then convolved and upsampled to try to reproduce the same original long acceleration vector that we had in the first place. Another approach that I considered here, and that seems intuitive given that we're working with time series data here, is to use some sort of recurrent layer like a long short-term memory layer. So here, the similar in the beginning, uses a couple one-dimensional convolution layers and max pooling to kind of downsample a little bit before getting to the LSTM, and then the LSTM does the final encoding step to get that smaller dimensional vector in the middle, and then also does that first decoding step and then gets upsampled by a couple of one-dimensional convolutional layers. So looking at the performance shown here is the training loss for these two different network architectures. I also played around with different sizes of input, different sizes of the encoded vector. Those varied mostly in ways that you would expect, but for the most part, it didn't have any drastic effects on performance of the model. So from here out, I'll show some of the results of the outputs and the visualization from just one of those purely convolutional models. So here we've got a couple examples of the outputs from the decoder end, shown in orange, versus the original inputs, shown in blue. For the most part, they kind of line up. The decoder outputs are essentially kind of presenting a filtered version of the original signal, which makes sense because we broke it down into much lower dimensional representation and then tried to reproduce it. Unfortunately, this may not work quite as well as I hoped because we're losing a lot of the high frequency component that may be important for picking out tremor. And we'll take a closer look at that in the next slide. So now we get to the meat of what I really want to try to do here, separating out, see if you could separate out data that only really looks like tremor and is totally distinct from activity recorded when there was no tremor at all, and use that to maybe identify what does a tremor really look like and what's the best representation of it. Unfortunately, as you can see here in the orange, there's a tremor, and the blue non-tremor. There wasn't really any kind of clear separation that came out of these. These are t-distributed stochastic neighbor embeddings during a couple, for examples pulled from a couple different tasks. And for the most part, the only real distinction we got here was it kind of tended to separate based on total activity here. So in sitting, there's a lot of examples in that long tail in the embedding that are just low activity. And then similarly in walking, most of it's really high activity, and those all end up clumped together. And there's a tiny little bit of low activity that's all clumped together too. So as I mentioned, I didn't quite get the result that I was hoping for here, and being able to really cleanly pick out a clump of um, encoded representations that could really clearly be identified as tremor and separated from everything else. And there's a few reasons I think that may have happened. For one, as I mentioned, I think a lot of the high frequency component that might be important for picking out tremor versus other kinds of movement um, is kind of getting washed out in the course of the encoding, and that could potentially be addressed by using a um, larger dimension of the encoding vector. And then another thing that may be helpful here would be to remove some of the low activity data that just definitely doesn't represent tremor, probably doesn't represent much movement at all, and creates kind of this trivial distinction between high and low activity that's maybe masking some of the more subtle distinctions that I'm trying to look for here. So those are the kind of concluding thoughts for my project. I really enjoyed working on this, working in the class. Thank you for your time and listening to this.